In terms of an overview of what I'm going to present this afternoon or this morning, depending where you are, we're going to start with how fast is fast, which is a relative problem, and what are the problems with monitoring fast reactions. We'll move then on to looking at techniques for in situ analysis of reactions, and I'm going to particularly focus on the stop flow technique. I'll give you a brief introduction to those of you that haven't come across the technique before, and try and highlight the limitations of the classic A+B type stop flow technique. And that hopefully will lead us on to looking at the benefits of a variable ratio multi-mixing system, and how this provides benefits not just in terms of time but also in terms of efficiency of materials required. And then we'll move through to working at how one can interface that with infrared for a new stop flow infrared system, and also then with NMR for the so-called Insight Express. And to illustrate some of the benefits of this, I'm just going to show you a few graphics of kinetics we've obtained in two reactions, one of which being CF3 transfer, trifluoromethyl transfer, and the other protodeboronation. So how fast is fast? Well, that depends on what type of chemist you are. If you're a physical chemist, nanosecond might be very fast. If you're a synthetic chemist, something occurring on a matter of minutes or seconds would be a very fast reaction. And the first slide I'm showing you is just an overview of a recent study we've completed on protodeboronation. And at the bottom on the left you can see some simple aromatic and heteroaromatic substrates that undergo very slow protodeboronation. They have a half-life of weeks. In the middle is one that's relatively fast, half-life for seconds, and one at the top is very fast protodeboronation. And so if we use protodeboronation as a reference frame for deciding what is slow, medium and fast, I've just picked some examples here going from a half-life of 10 hours to moderately quick 10 minutes, something you have to take samples fairly quickly from or analyze in situ, through to something that's very fast and that's going to have to be analyzed using specialized techniques. So what are the techniques and what are the problems? Well, the problems that have to be solved are acquiring data fast enough, so it's an issue of density of data. If we go back to the previous slide and look at the fast reaction on the right, you can see in that reaction we've only been able to acquire about 7 or 8 data points over the period of 2 seconds. And not quite the data density one would desire for that type of analysis. It's also an issue of initiating the reaction. One wants the reaction only to start when required, and it needs to be completely initiated all at the same instant. We need to control the temperature during the initiation and the reaction. We need to precisely assemble the reaction. We need the right volumes and therefore the right stoichiometries of all the components to ensure that we're monitoring the process that we think we're monitoring. And finally, and perhaps a point that's often overlooked, it needs to be completely homogeneous. We have to have mixed completely at the point of initiation. And this can be a problem, especially in very small reaction vessels, one of which, a classic example of which, is an NMR tube, which is a long, thin reaction vessel if you're doing the reaction in the tube. And I'd just like to share with you an example of very poor mixing, not deliberate, but an example we found recently. So this protodeboronation of this difluorinated boronic acid is initiated by adding hydroxide, and adding hydroxide to the boronic acid sets up an equilibrium between the boronic acid on the left and the boronate that's in the centre. Now, the rate of that equilibrium is extremely fast, and so at the NMR timescale you see single time average shifts for whatever nucleus you're looking at in that molecule, and that rapidly equilibrating system undergoes protodeboronation with a half-life under these conditions of about 20 minutes. So if you look at the fluorine NMR of this system, you should see single peaks. And indeed, if you look at the bottom 2 NMR spectra in this slide, you can see we see single peaks corresponding to the boronic acid at the bottom, equilibrium mixture between the boronic acid and the boronate, and the second spectrum up. But the top 2 spectra show distinct peaks for the boronic acid and the boronate, both of which are present in the NMR tube, which tells you immediately that there are distinct zones within that tube, as highlighted by the cartoon on the bottom right, regions of different pH. And this is even though the tube has been fairly vigorously shaken after addition of the base. So attaining homogeneous complete mixing is an issue that has to be carefully attended to.